was this constrained problem. X.
Just a quick question.
Yeah.
Is anyone scribing today? You ready? Great.
All right. Remember, I'm being super lazy here, right? Because this, what is this actually? This is sum over I. So I'm being lazy and not writing that out, but that's actually what's going on, right? F is a function, right? It's a function of x. Okay, what was our example? What was our example problem?
A dice.
We had a dice. Dice was not a fair die. In the sense that the expected number of dots that we see is 4.5, I think we said. The example was where f is just a function that, in this case, f is literally the function I, right? If you index by the number of dots I, then. Okay, and so we set up a Lagrangian for this problem. P minus gamma sub P minus 1 minus lambda right? And this is the magic trick of Lagrange multipliers. I'm sure you've seen it at some point before, although it's probably been a while. And roughly intuitively, the reason it works is if I try to find the optimum with respect to lambda or gamma, I just, for that to be true, to get an optimum, these constraints actually must hold, right? It must be that sum P equals 1. That's the kind of intuitive reason. Okay, and so now what we're going to do is we're going to try to find the P that optimizes this. Okay, that's the trick we're going to do. And so how do we find the P that optimizes this?
Divergence with uniform distribution.
You
said there's a dual problem?
There is a dual problem, yep, and we'll get to the dual problem in a minute, but if I want to figure out what the optimal P is, right, given the lambda and gamma, what can I do?
Gradient equals 0.
I can set the gradient equal to 0. Good, the gradient with respect to what?
The P, lambda, and gamma.
We'll do lambda and gamma later, okay? We're just going to do P for now. And remember, P is a vector. Why is P a vector? It's not a single number.
Probability of
The
each.
probability distribution.
Of coming up 1, coming up 2, coming up 3, coming up 4. Okay, so let's compute, I'm going to call this whole thing up here L, Lagrangian, L, Pi, meaning with respect to a particular die, like the side comes up 3. Good. Okay. Let's do the easy terms first. Okay. And then we'll do the one that requires a chain rule. Okay, very complicated. So what is the derivative of this term with respect to Pi? Some particular Pi. First notice that minus gamma times minus 1 is not a function of Pi, right? So it doesn't matter. Right? I'm actually only caring about this. What's the derivative of this thing?
Times gamma.
Good, why?
The sum of P, I take partials with respect to every P.
Yep. Right, so what is this thing actually? This thing is actually P1 gamma times P1 plus P2 plus P3, so on and so forth, right? And so if I take the gamma with respect to one particular one of these, let's call it Pi, then I just get gamma. So first term is gamma, Okay, what about this term over here? And it's minus gamma, right? What is this term really? So again, minus lambda times minus c is not a function of pi, so it's really just minus lambda times what? It's minus lambda times p1 times f of x1, right? Plus p2 times f of x2, so on and so forth. Good. If I take the derivative with respect to a pi, what do I get? What is it?
xi.
F of xi. And
I
it's-
mean lambda
But it's
f-
minus lambda f of xi, right? Minus lambda f of xi. Good. Okay. Let's do the hard one. Minus p log p. Okay. What do I have to do this one?
Chain rule.
I have to do the chain rule. Good. Okay, so let's do both terms. Pick whichever one you want to do first.
I think it's ln p plus 1.
Is minus ln pi. Good. And that comes from taking the derivative of this piece times this piece, right? Because the derivative of pi is just 1, right? Or minus 1 in this case. And then I got log pi. Good. And then there's another term, which is I say p, and then I take the derivative of log p. What's the derivative of log p?
Oh,
Which cancels with the p. And so the final answer is, I think, minus 1. It actually doesn't matter, but. Positive 1? I think it's minus 1. Okay. And now what do I have to do again? The whole point of the second derivative was I was going to do what? I was going to set it to 0, find the optimum. Okay. So if I rearrange everything, I can get log pi over on this side equals minus gamma minus lambda f of xi minus 1. Okay, the minus 1 is basically just totally irrelevant. I can put the minus gamma and the minus 1 together and just call it a new variable. So I'll call it minus gamma prime, okay, where I'm just defining gamma prime equals gamma plus 1. Okay, I didn't change anything by doing that. As I said, the 1 is irrelevant. Minus lambda f of xi. Okay, why is gamma there again? What purpose is gamma serving?
Enforce that P is a probability distribution.
Enforces that it sums to 1, in particular, it's probability distribution. Good. So if I exponentiate both sides, I get what? I get pi equals e to the minus gamma prime minus lambda of f of xi. Okay, good. But remember, the whole point of this gamma thing, I can actually tell you what the correct gamma is, in fact. And the whole point of this gamma thing was to enforce this constraint that the p sums to 1. So I can just tell you what it is. Okay? In fact, I could just rewrite this as e to the minus lambda f of xi over z lambda. I'll often ignore the dependence on, I'll often just suppress the dependence on lambda because I'm lazy, right? But it is in fact a function of lambda. Where z lambda is what? What is z lambda? This thing has to normalize. It has to be a probability distribution. What does it take to make this thing a probability distribution? What do I have to divide by?
sum of exponent.
Sum of what?
Close all PAs.
E to the minus lambda f of xi, where the sum is taken over the i's. Right? That's what makes it normalize, okay? And so gamma is just the log of this minus the log of this, right? Whatever it takes to make e to the minus gamma equal z, right? Equal 1 over z. Okay? Does that make sense? Okay, so this is kind of somewhat remarkable, right? In a way, we've actually done the most important part, which is this piece right here. I know the form of the optimal solution to my nice problem. Okay. What it looks like is e to the minus lambda, in this case, the f is just I itself, right? It's just the number of dots that appear on the face. Okay, so for our particular problem, it looks like e to the minus lambda I normalized, whatever it takes to sum these up and normalize them, is the probability of I. Okay? Does that make sense? Okay, so let's do a couple values in our head so we have some idea what's going on. So if I took lambda equals 0, what happens? I don't know what the right lambda is, right? There's a free variable here, which is lambda. What happens if I do lambda equals 0?
You have equal probability to all the events?
Yep, I have equal probability to all events. Okay, so that does not notably meet this constraint, right? It would not have, in fact, it would have the expected value of 3.5. Okay, so that lambda value is wrong. What if I take lambda, by the way, the minus sign is just convention here. It doesn't really matter that it's minus or plus. Okay, it's convention because in physics, this F is going to be energy. And it turns out you're going to have higher energy configurations be less probable. That's the origin of that convention. So what if I pick lambda equals very large, gets close to infinity, what happens? What does this probability distribution want to do?
The probability in one instance.
I'm sorry?
All the probability converges to one.
Which instance? Well, I is going from 1 to 6 in this case, right?
One.
Yeah. It's going to put all the mass on the smallest value. If I pick lambda equals minus infinity,
The highest entry.
it's going to put all the mass on 6, the highest value. Okay, so we know in fact that the answer is going to lie somewhere between 0 and minus infinity. Okay, we could just search for this number, right? We could just write a 1D search to go find this number, and that would be a fine solution. But I want you to picture in your head what it actually looks like, right? We're going to have a distribution 1, 2, 3, 4, 5, 6, and it's going to look like something of the form of this, right? Drawing a very poor exponential. Okay. Growing faster than that. It'll look something of this form. This is the maximum entropy distribution for this dice problem. Does that make sense? Okay. And so the only question is how to find lambda. So the obvious thing to do is we start with a guess of like 0, right? And then we go try to change lambda. And in fact, we need to change it, looks like in the minus direction, until the expected value of this distribution equals 4.5, right? So we could just test until we get it equal to 4.5. It's a root finding problem. That would be one way we could solve the problem. Does that make sense? So we're in principle done, and now we have a 1D optimization problem instead of a 6D optimization problem. That's the thing that's cool about it. Okay, but we can actually compute, there's actually an easier way to solve it, and we're going to do that, which is we can take this thing that we computed, this form of the distribution, plug it back into here, right? Because we now know the optimal form of P. Okay. And then we can solve for the lambda value that we need. Okay. And that's computing the dual problem, which is I'm going to substitute this back in and solve just in terms of lambda. Gamma is actually eliminated because we already made the thing normalized by itself. An important thing to note, someone pointed out last time, came up after and pointed out last time, that I left off the constraint. What constraint did I leave off? Left off a very important constraint.
Lambda and gamma greater than 0, greater than equal to 0.
I don't think that's true for the equality one. For inequalities, that would probably be true. But there's a constraint on P that I left off. I left off a constraint that P is greater than or equal to 0. And I did that because I knew that if I solved this problem without that constraint, the solution would come out enforcing that constraint already. And if you have a problem where you don't enforce the constraint, but you get the answer and the answer already has the constraint, then adding the constraint doesn't do anything. There's a name for this. I don't know what this is called. But adding a redundant constraint doesn't change the answer. So I cheated. I knew the answer would come out, so I didn't have to add it.
But like ln cannot take negative values, so it wouldn't have.
I'm sorry?
The log term couldn't have taken negative 3 values.
Would we have predicted without looking at the solution?
I don't know that I could have predicted it. maybe there's a way to know that it was gonna come out that way. It's not obvious, it was not obvious to me that it would come out that way. But you could add the constraint, it would end up being slack. And so, because it's already these are already positive numbers, right? E to the minus lambda f is always gonna be a positive number. Okay, so what do we have to do? We have to go plug back in. This is where the chances of getting it right get increasingly small. That I don't make an algebra mistake somewhere in this calculation. Okay, so we're just plugging this in for p here, okay? And again, I'm going to cheat because I know some things are gonna come out. So if I do minus some p, I'm not gonna substitute in for this p. I am gonna substitute in for the next p. If I do log of this distribution, what do I get? I'm just computing this part right now.
Negative lambda fxi minus log z lambda.
At some point, I'll stop writing the lambda. Good, okay. This is already 0 because I already made it sum to 1, so I can ignore that. The remainder part is minus lambda sum df minus c. Okay, good. Notice this term and this term, what's gonna happen? This piece right here is actually plus lambda, the expectation, plus lambda, the expectation of f, right? This is also, this is minus lambda, expectation under p of f. Okay, those two just cancel. Good. And so the whole thing boils down, this is not a function of p. I can pull it out, right? So that it's minus, actually plus log z, sum p, right? What's sum p? 1, okay? So that whole thing boils down to log z lambda. Hopefully I got the sign right. Okay, and the last term is just what?
Lambda c.
Plus lambda c. Okay, hopefully I got the sign right. So that's the whole thing. This is the dual problem right here. So we're optimizing this in terms of lambda. To find the right lambda, I just have to optimize this problem in terms of lambda. What do I do if I want to optimize a problem? A nice smooth problem.
Gradient to 0.
Yeah, first I'm just gonna compute the gradient, but we can also just set it 0. Sometimes you can't analytically solve for the gradient equals 0, so you just need to say do gradient descent, or some fancy variant of gradient descent. This, by the way, is called the free energy in physics. It shows up everywhere. I can't remember, up to sign and up to some constant that they put in front of it, like Boltzmann's constant or something like that. But this thing is called the free energy, because it's the most important quantity in statistical physics. Okay, I'm gonna compute the gradient of this thing, and then we're basically done. I'm just gonna show you like 2 examples, and then let Stephen teach you the wonders of weighted majority. Okay, so if I compute the gradient of this thing with respect to lambda, what do I get? I get a c, right? If I compute, now this is the magic trick. If I compute the gradient of this thing with respect to lambda, so I'm gonna go d lambda of this thing. It's just one variable, right? What happens when I do the derivative of a log? What do I get?
1 by
What is it?
1 by z
1 over z lambda? Good. And then the derivative of the inside. What's the derivative of the inside? So it's the derivative with respect to lambda of sum of e to the minus lambda f, right? Because that's what z is, right? Z is just the thing that makes it normalize again. What is the derivative of this thing with respect to lambda? The minus is going to pull down and the f is going to pull down, right? So this thing is equal to 1 over z lambda minus, and that minus sign is making me very happy. Oops, I already computed the gradient of this, right? minus f times e to the minus lambda f. Great. Does this look like anything? If I rearrange this slightly, what is this?
Expectation
Yes.
times.
Put this z in here.
Yeah.
Then this thing is actually the probability p again, right? So this whole thing, and then what was it? Was it plus c over here? So this whole thing is actually equal to minus the expectation under that probability distribution for our current value of lambda, whatever our current value of lambda is, of f plus c. What is the value of c again? 4.5. It's 4.5 in this particular problem, but in general, what is it? It's whatever our known expectation is, right? We know the probability distribution is supposed to have this constraint. So what this thing is literally says the gradient of lambda is literally just the difference between what your current, you have some current value of lambda, what your current expectation is and what it's supposed to be. Which is pretty awesome. It's the obvious thing. It's just the error in your expectation. And so now you update your parameters by that. Okay. Turns out bazillions of problems are maximum entropy problems. This probability distribution family is called the exponential family. Okay, it shows up everywhere. What problems are maximum entropy problems? So almost all the outputs of neural networks turn out to be maximum entropy family forms. And in fact, you're optimizing the likelihood of those maximum entropy. Almost the majority of statistical physics, classical statistical physics, has this form. So to give you I'll give you two concrete examples. Concrete example number one, it's called the exponential error problem. Exponential error problem. So the problem is, you've got a gas above the Earth, okay, like air, okay, and you want to know what's the probability of finding a molecule of air at some particular height. Okay, that's the problem. So the most basic data you have is that the potential energy, the expectation of mgh is equal to some constant, some average expected energy of this. And then what is the form of the distribution probability of height that you should associate with, given this one piece of information? I very blithely passed from discrete variables to continuous variables in this case. Just imagine that heights are little tiny slices, delta h's. Okay. What's the rule? It always looks like what? It always looks like e to the minus lambda times whatever the function you're taking the expectation of. So it's going to look like e to the minus lambda mgh normalized. Okay. So the probability, and this actually turns out to be true. So the density of air, which is basically the probability that you're going to find a particular molecule at any height, falls exponentially in the height above Earth. Kind of interesting thing. It's quite subtle because there are different kinds of molecules in air. Air is not a single type of molecule, right? So they have different m's, and the temperature also varies with height. Yes?
Is the continuous version of this just the Gaussian distribution?
No, this is like the Laplacian distribution. It's like a one-sided Laplacian distribution because there's no air below ground, right? So there's an implicit constraint there that you're summing with zero. Let's do the one you just said. What if I tell you I have a gas? I have a 1D gas, and that gas has the property that its mean velocity is 0, okay? And its mean kinetic energy is some value, which we basically call temperature. So the mean kinetic energy of a gas is basically its temperature, okay? Is 1/2 mv squared equals some constant, which is proportional to temperature, okay? Then what's the probability distribution? Turns out the generalization of this, if you have multiple constraints, is just to add multiple lambdas, one lambda for each of these constraints. Okay, so the probability distribution that meets this form looks like e to the minus lambda b minus 1/2. I can just pull these constants out because these the m and the v are just constants, and shift them over here, so it looks like 2c over m minus 1/2 v squared. Okay, normalized. Okay, so again, just imagine the velocities are discretized into little bunches, okay, and then take the limit as you take those things to 0. Okay, or equivalently, you're optimizing the continuous entropy integral p log p. Okay, yes, that's continuous version. This is a Gaussian. You probably not used to seeing it in this form, but anytime you have e to the minus a quadratic, you have a Gaussian. Okay, and if you want to put it in the form you're used to, you have to complete the square. That's basically what you have to do, put it in the form which looks like a mu and a sigma. Okay, but this is the distribution in a one-dimensional gas. Okay, and the velocities are in general distributed according to exponential families. So those are 3 examples that we went through. I think I will stop there except for to say one more thing. Connection between between maximum entropy and frequency. Okay, so here's a very fascinating result. It's chapter 12 of the Covert Thomas book. It's actually one of the best chapters I think I've ever read of a book. It makes this point, as does Jane's. So if you imagine you do a large number of trials, like we roll a die many, many times, okay? And I tell you that the average of those rolls is going to come out to 4.5, like in our example, okay? Then you can basically ask the question, combinatorially, how many different rolls are there? Phrasing that poorly. How many frequencies of rolls are there? So we've got a probability distribution P that maximizes the entropy. Okay. We have a frequency F, okay, which is, think of this as the ratio of number of rolls that come up I. Okay. So imagine I do 1,000 rolls of a dice. Okay, and I look at how many rolls come up 1, right? Maybe it's 100. Okay, then the frequency F, it would be 100 over 1,000. Okay. If this distribution F, this frequency distribution F meets the constraint, okay, then the number of different ways that you can realize that constraint falls exponentially fast as you move away from the maximum entropy distribution. So almost all frequency counts of 100 over 1,000, almost all of the ways that the dice can roll end up being close to the maximum entropy distribution if the constraint holds. Okay, and so the question for you guys is, well, doesn't that mean it's just always realized? If I give you this information, isn't there really only one probability distribution that can meet those constraints? The answer is no. Because in reality, there may be constraints that you didn't know about that are active, right? That you didn't know there was some additional information, and you get something which is actually very far from the maximum entropy distribution. If you see something far from the maximum entropy distribution, it means you missed some constraint, basically is what it's saying. There's information that you have not taken into account. All right, we're gonna stop there. Cool. Now we're gonna apply some more Hale divergence.
Cool. So I will take on the challenge of using the chalkboard. And magically, stuff already appear on it. That's cheating, okay. Well, in this course, and including this lecture, oops. All right. The idea of cheating will appear many times in this course, including today. One form of cheating is to have someone else, myself, writing out what's going to be the rest of today's lectures. Okay, so I thought about how to continue this topic in the best, with the best synergy. Actually, I think one way to think about the first topic we cover, online learning, is through the principle of maximum entropy. Okay, so for the rest of today, the goal is simple. So we're going to revisit the online learning problem with expert advice, And we think about how to solve this problem with the maximum entropy principle. Okay, so that's just that takeaway. But first, what exactly is the problem? Just quickly revisit. This is sort of an online learning problem, meaning you don't take a class on Zoom. You kind of learn as you make decisions. So alongside of your decision-making process, you have N experts you can consult. You can observe how they make decisions along the way. So there are N experts. You can almost always think of this capital N as super big. And every day, you're making some decision. And the way you make decision is basically try to follow one of the experts. And from Drew's lecture, you basically learned that a good strategy tend to be randomized, right? So you don't want to, fixate on one expert on any given round. You kind of want to hedge your bet a little bit. You want to place some probability on each of the expert, in case things turn around, right? So for this lecture, and because we already talked a lot about probability and entropy, you can almost always think about the algorithm playing or selecting some probability vector over the experts, okay? And then that's going to be useful later on for future lectures because you will be used to thinking about, different learning algorithm choosing different kind of parameters, okay? So here you can think about probability as some sort of parameter you can choose, right? Okay, so this is sort of a game that takes place over some number of rounds, let's say capital T rounds. At every round, little t, after you choose how you're gonna, pick the expert randomly, some adversary will review some loss vectors. So literally it just means like how to penalize each expert. Right? So some experts tend to do well, some experts tend to do poorly, this can be organized as a loss vector. And this is a randomized algorithm that you can think about the loss as the expected loss of your algorithm, which is like the sum of the probability you place on each expert times their loss. Okay. Good. Sometimes I might slightly abuse notation to write this as LT PT. So to get used to the idea of loss function, okay? But most of the time in this lecture, loss function is just linear. Okay, so you have seen some example of how to solve this, right? So I think in Drew's lecture, you can this algorithm called weighted majority. Majority is this variation of this algorithm often go by the name of multiplicative weight. Okay, so you might have heard of these sort of algorithms, but one way to do this is you initialize P1 to be something, typically a uniform distribution, and you just every round after you observed the loss from last round, the probability you put on expert I will just be proportional to 1 minus eta. Okay, so this is just a shorthand for proportional because I'm lazy. For describers in LaTeX, this is prop2. Okay, so this is usually a way to be lazy if you don't want to explicitly write out the normalization factor. At the end, this is a probability, so you want to divide by sum of these things.
You might call it Z.
You might call it Z. Yeah. Okay, so this is kind of the algorithm you have seen. I think there's some subtle difference that depends on whether you normalize at every step to actually get the probability for PT, or you just keep multiplying out the weights and only normalize when you use it. Okay, so we won't go into that subtle difference here. Today I want to actually present a different algorithm that basically is derived from the maximum entropy principle, but also is closely related to some idea that you feel like should almost work. Right? Okay, so the goal today is to apply max entropy. So how do we do that? So let's start with something that is simple. It's something that we kind of know it doesn't work, but it feels like it should. Right? So there's one algorithm that we know doesn't quite work because there's some interesting counterexample. One type of algorithm, with the simplest form, arguably the first algorithm you could think of is follow the leader. Okay, so what does it do? Okay, let me try to write it down. Like follow the leader, at round t, you compute. I'm going to use this parameter form because it's convenient. I try to, I want to look at which expert is performing the best so far, which is sum over t. We use tau as an alternative weight for time steps. Okay, that's it. I think. Yeah. Okay. So at round t, I'm going to look at. This is just another way to say, I look at different ways to put probability on these experts. Different way to allocate these probabilities will incur some cumulative loss. So this notation is really just like the cumulative loss had you been playing fixed p so far. You've been playing the same probability vector p so far. Okay, this is maybe a slightly cumbersome way to write this, because the answer to this argument is usually a single expert. Because this is a linear optimization, you actually just put all the probability on the single expert that have the smallest cumulative loss so far. Okay. Why doesn't this algorithm work?
Collapse to point measure, just one peak distribution if you choose R.
We'll have one peak distribution. What's wrong with that?
Because you want to maximize entropy.
Well, I like applying the principle of cheating by knowing. Anyone else? Yes, I would like to apply at max entropy, but before I tell you that, why would this not be a good idea?
If any algorithm is deterministic, the adversary can accordingly assign the losses to all the experts.
I see. So good. So let me repeat what you said. If my algorithm is deterministic, which will be the case because this is a linear objective, Arcmin will actually put all the probability on one expert. The adversary could always screw you up. Whenever you decide one expert is good and bet all your money on it, the adversary can actually put all the loss on it and set the loss for other expert to be 0. Okay. So good. So this doesn't quite work, but we'll we'll think about this algorithm a lot today. Instead, I'll tell you a different algorithm. It's called follow the regularized leader. Okay, and it's almost the same, except that obviously you would like to apply the max entropy principle. So here I would like to maintain sort of the cumulative loss so far. This is a place where I might screw up with sign. Negative. Okay, so where this H is supposed to be the entropy. I think there's a negative sign here. This is the entropy. Okay, I hope I make even number of sign mistakes. Time will tell. All right. So, by the way, like, you know, with the fun exercise we just went through with Drew, like, you actually, this is actually, there's an alternative form for this, like, you know, one way to think about this is there's like a solution, there's a closed form solution for this will be this is proportional to exponential So how is it related to the exercise we just did with Drew? Well, you can almost think about this form as kind of like the Lagrangian you would have written down, except now you actually get to choose the Lagrange multiplier. Like this this 1 over eta used to be what Drew might have called lambda or gamma. And you can sort of apply the same intuition for this problem. Right? So for this problem on line learning. At round T, you have observed how these experts make decisions so far. You have seen how they perform, how well they do. You know, maybe Santiago has very little loss, like, you know, Gogo has tons of loss, you know, my PhD student. Well, you know, should I bet all the money on Santiago? It's not clear, right? So like, so this is a case where you would like to go with the current evidence you have, which is like the cumulative loss for every expert. But you also want to hedge a little bit to maintain some amount of uncertainty. That's where you tag on this entropic regularization. So this is sometimes called regularization. The thing when it's used as an it's like adjective is called entropic. Okay, so let's understand how this algorithm works. Good. So there's basically different ways to prove this algorithms. I will basically show one proof strategy or one way to think about this algorithm using entropy as a method to ensure stability. Okay, so this will be a repeated theme in the proof, but I will show you mathematically. But really, there's sort of the key idea is like how to use entropy as a stability term. And intuitively, it makes sense, right? So like the reason that follow the leader could fail is is too greedy. Like as soon as I see some leader is going ahead, I bet all my money onto this leader. But that the leader could change over time, and like whenever the leader switch, I suffer the loss, right? So the idea is maybe I should be less jumpy. Right? Like I should not jump around and just like bet all my money on someone who looks going slightly ahead. And this is kind of what the entropy term is doing for follow the regularized leader. Okay, so and we'll try to analyze how this stability effect come into term. So there are a couple of things I want to define. So I'm gonna define what's called the optimization procedure. Actually, I'm gonna call it oracle. So I'm gonna simplify notation and call this thing out of L1 through T, argmin of T. Okay, so this is sort of what you imagine all the leaders do around T plus 1. Okay, I want to have a switch of perspective. Okay, so we know follow the leader is not quite good. It's not quite enough to solve your problem. And I'm going to apply the principle of cheating again to think about like an alternative way to solve the problem. Okay, so follow the leader doesn't quite work. I want to introduce a different idea, which is called be the leader. So here's the lemma. This is something called be the leader. Okay. So let me write it, in mathematical form, and then once you stare at it, it will make sense. Right? So what is be the leader? Be the leader means like you actually get to see the loss of today. Okay, so it is cheating. Like it's not following this pseudocode. It's like a hypothetical algorithm where you show up, the adversary slowly, like quietly whisper the loss of today to you, and you can actually think about it and make decision on top of it. Okay, so the loss of this algorithm, or the algorithm effectively, is applying this oracle at round t. It's cheating because it gets to see the loss of round t to choose like the p, right? So this is the loss. Okay, so what's going on here? This algorithm is a funny algorithm. It's a hypothetical algorithm. This is sort of the be the leader. Oh, this chalk is definitely less good. Okay, so what this is saying is, at round t, I'm gonna pretend that I actually have the loss for today, and I will choose the expert that's doing the best so far, including the loss of today. So again, this is a hypothetical algorithm that you don't get to play because you don't get to choose your strategy before you see the loss, right? But this is what you get for beta leader. This is sort of the best expert in hindsight. Okay, so this is like after all their interactions have taken place so far. Okay, so I look at round 1 through round capital T. I look at the history. There's one expert who does the best. This optimization oracle, by looking at the history, will choose that expert, and that's the cumulative loss of the best expert. Any questions so far? Yes, please.
Understand the notion of be the leader over here. So you are calculating the loss beforehand and then choosing the expert, or?
Yeah, so this is a hypothetical algorithm that get to see the loss of today, and of course you get to see a loss of previous rounds. And by looking at these total loss, you get to choose the best expert.
Right. But a follow-up over there would be, even in the expert in hindsight, we are summing till t, so technically we are seeing the loss till of today.
This is also this one, right?
Yeah.
So this one is like what you would like to compare to.
Right.
This is not what you're trying to play. Like this is like after all that happened, looking back, Goko is the best expert. I should have matched this. So neither of this is what you play. Neither of this is given your algorithm. I think you first, yeah.
So if you already know, like in the be the leader case, if you know what is the minimum loss going to be for today, why do you need to look at the history?
Yeah, so it will show up in a bit. It's deliberately, I deliberately overkill a little bit to include a history as part of this, because this is not too far from be the regularized leader, which is not too far from follow the regularized leader. So there are two more steps in the proof, and it's a couple of proof. Yeah.
So the reason the right-hand side is greater is this one can only choose one.
That's right.
But this one can
That's a great observation. Yeah. So there's a proof. I don't think I have time to prove it. The proof is proved by induction, but it's not hard to believe because this side has more flexibility. You actually choose different strategy every round. It does have a little bit baggage with this. You don't carry the history with you every step. You cannot myopically just optimize LT for a single round T. But it's not surprising this will do well. Like this is like, you have the flexibility.
So the fact that this is smaller, is that good or bad? What is the impact?
It's fantastic if you get to cheat.
But this one is doing even more cheating. Like it's its entire history, and in retrospect, it choose the best.
Yeah, so but the nice thing we would like to claim at the end, we will approach this target at the end. So yeah. And the way we show that is by showing that we're actually not even that far off from this cheating algorithm. So I will not prove this. The scribers can ask me for proof, or you can just prove it yourself. Proof by induction. That was not proved by intimidation. Okay. Great. Here comes the most interesting part, in my opinion. So this is about be the leader. I'm going to call this out. The algorithm we actually have is called follow the regulars lead. Okay. Oh, I guess I didn't write down the regret definition, but so the regret of FTRL is less than so in case there any ambiguity, this is generated from FTRL. Okay. So I would like to prove this. So this is sort of the goal, and I want to use this fact. Okay. Here's a thought experiment. This is pretty cool. Like, this is no regret. Like, this is an algorithm with no regret. It's not quite the algorithm we have. I want to somehow have a change of perspective so that follow the regularized leaders kind of look like be the leader. Okay. So there's a proof. Yeah, go ahead.
I didn't completely understand why do we have long term before the difference of losses between time steps?
There's a log term?
Yeah, the long term log and
Yeah, I'm gonna show you.
you will-
Yeah. Hopefully. Yeah. I'm gonna fix let p star equals. Okay, so this is the thing I want to compete against. The expert that get to see the entire history of loss and then, do the best, right? So. Well, so what's the difference between be the leader and follow the regularized leader. Okay? So it's sort of off by one step, right? So like, you know, be the leader just happened to know a step, it's just happened to be a step before you. Okay? So I'm gonna try to match my best as I could, like, you know, what be the leader looks like, right? So you can think about what the algorithm look like if I try to think about the entropy term as an initial loss. So before round t equals 1, there's another loss that somehow I get to show. So you know, pretend L0 equals, okay? And I want to first think about like a scenario where like, you know, there's a be the leader algorithm that also taking an extra step of loss before round t equals 1. Okay? So, you know, and then you can gradually see why, oh, I guess there's a negative. Why I want to do that, because in the follow the regularized leader, this is the extra term I tag on to the cumulative loss. And the way I think about this is, you know, why do I think about this as an extra round that I have? And, you know, then be the leader and be the regularized leader are kind of the same thing. Okay? So, so instead of going from round 1, I'm going to start with round 0. Okay? So this is okay. So what happened here? So this is the be the leader with the regularization. Okay. Oh yeah.
So does the dilemma holds for like a convex loss? Because I thought like the entropy is not a linear.
Oh yeah, it holds for convex loss. Oh yeah, good point. I didn't prove it for convex, but it holds for convex loss. So this is sort of be the leader. If you account for the extra round 0 of the regularization. So you can almost think about this as be the regularized. Yes. And be the regularized leader is only, according to this lemma, it's only better or never worse than, you know, the best in hindsight. Okay. this. This is sort of the best in hindsight. It's actually not quite the best in hindsight if you account for a t equals 0, but this inequality holds. Okay. And conveniently, this thing is just what is this term? So again, this is like, look at the loss up to round t, add another regularization term to the loss objective, and optimize fully. What is this term?
E star plus some constant factor, or
E star, sorry, say again?
E star plus P0?
E star plus P0.
Plus L0.
So this is like, look at all the loss up to round t, add another L0, but L0 is just like this term. This is like what you will play for next round. This is like this is the so-called beta regularized beta because it's what you would have played if you get to look at the loss of this round, which will happen actually on the next day, on tomorrow's observation. Okay. So the proof basically is quite there. Like this is a statement we would like to prove. We basically get these terms that looks like the differencing term between PT and PT plus 1. You might wonder where does log n over eta come from. We're going to do that now, but it really basically comes from the fact that this is starting from t equals 0, not t equals 1. We basically pretend that there's a round 0 where the loss is the entropy. And now take it out. Now, basically, we just need to take it out. So go in this direction. So what we get is the regret P1 through T. Again, now we start with round 1, not round 0. Plus L0 of P0 minus L0 P star. Okay, so what this inequality is showing, this is no more than so the goal is to bound this term. And there's some cancellation I get, but the regret of P1 through T is no more than, what do I get? L0 of P. So this is a key lemma. Yes.
Why is L0 P star not?
Yes. So what is this thing, right? So this is like L0 again is like -1 over eta entropy. Like one of these two terms has to be non-negative, and one of them has to be bounded by maximum entropy, like how big entropy you can ever take. So this term, how big can this term be? Which is so there's a multiplier of eta. So okay, so I know it's a lot of math, but what has really happened so far? Okay, so just to remind you, so far, be the leader is no regret. Okay. We don't get to play that. Okay. This lemma is showing you what exactly is showing you. This is what you play around T. PT is what you play around T. Let's follow the regularized leader. PT plus 1 is like what you play in the next round by looking at the loss, including today's. Right? So this is sort of saying the regret is less than some blah plus loss difference between be the regularized leader and follow the leader. Follow the regularized leader. So, and this is sort of useful for proving this because the way I prove this, like, be the regularized leader is actually not that different from be the leader if I pretend the regularization term is an additional loss, like around 0. Okay. And what's really left for showing this kind of regret guarantee is like, how big is this guy? This still seems kind of big, like, it's just like summing from round 1 to capital T. This is what people usually call the stability term. Okay, and I've been hinting at it like a while ago, but this is like, in principle, hard to control. Like, this is summing over T terms, like, it could grow like T. But if you actually have the entropy regularization, PT and P plus 1 cannot be changed by too much. Okay. Okay, so why is that, right? So you can look at the form of PT versus PT plus 1. Okay, so what is PT? PT looks like this top right. It's like sort of allocating probability proportional to the exponential of the cumulative loss for each expert. Okay, so you can do the mental mapping for PIT plus 1. Okay, so what is the PIT plus 1, which is, instead of taking the sum up to t minus 1, you sum one more term. Okay? It's not that different. Most of the things are the same, like you just shifted the exponential for every expert by a little bit, and most by e to the eta. Okay, so this is proved by staring, but this one intuition you should have is because of the entropy regularization, you cannot jump around between different distributions too quickly, right? So because the loss between rounds for every expert, the cumulative loss can change at most 1. And because of that, this term cannot be too big. Okay.
The losses are bounded by 1.
The loss is bound by 1. Okay, so I'm gonna state without proof, but the final piece is really stability, where if you compare the sum of the losses, use PT to be evaluated for round T versus the cheating algorithm, which is like choosing, based on the loss of today as well. They're not so different. Okay, so. So this used to be e to the eta minus 1, but approximated by 2 eta. Okay. Yeah. The final step is really like, it will be just summing the log n over eta term with this thing. The summation is no more than t. Okay, so if you set eta to be probably something like log n, then the regret bound we're 1 minute over. Happy to take questions, or people can enjoy the code outside.
You just kind of right board like where the L and over came from?
The log n over eta?
Yeah.
Yeah, so this is just the entropy term. It's entropy over eta for the probability. So L0 is the entropy of P over eta. Entropy can be bounded by log n, where n is number of experts, because these are probability distributions over n things.
Like specifically the entropy of the uniform distribution log n.
That's right.
Yeah, that makes sense.
It's cheap. I don't think I use Z ever, even though it's strongly suggested by Drew.
Question? I didn't completely understand why should that be less than or equal to T? LT of PT.
Oh, it's just because LT of PT for every T is less than 1.
Is that a definition or?
Yeah, I should have assumed it up front, like, yeah.
Okay.
It's just bound, you have to assume sort of bounded loss, yeah.
So otherwise, if you didn't assume there was an upper bound of 1, you would pay for the scale of the loss, you're just ignoring that factor.